This is part 2 of my CNC project where I built a functioning CNC milling machine out of a machine frame that I purchased. As you can see, the machine is in a different spot now. It's where it belongs, it's sitting next to my PC, and it has already a spindle mounted. Also, it did some movement and it also made its first chips. I might not be an electrician, but I'm a mechatronics guy and I know my way around industrial automation electronics. And while I was here putting some plugs on some cables, I thought I'd show you my electrician tool set or toolkit. I keep it in a parachute bag. This is one of those bags that you normally put in a bucket and you get some compartments. But I like it, you can zip it up pretty tight on top and then it's just a nice small package ready to go. And this has everything for wiring on machines and also most of the stuff I need when I do a little bit of wiring work around the house. What do I keep in there? A multimeter, which I use 99% for continuity check, and the rest is voltage, resistance and current. But most of the time it's just continuity checker. It's an X-Tech. I would prefer a Fluke because their continuity checker is a little bit nicer, but this is also a nice meter. Really, don't hate it. I have in there a set of wire strippers, Weidmuller stripbucks. These are the only wire strippers that you will ever need. They work on extremely thin wires and also on thick wires. Solid core and multi-strand wire, no problem. And also they have an excellent wire cutter on them. Crimper for ferrules. This is an Ipex crimper. This is the serrated style. There are different types. Everybody has different opinions on which is the best. This creates a square cross section. There is a hex cross section too. I like the forward facing ones because you can get in tight spots. The sideways facing crimpers are a little bit harder to get into places. I keep a larger crimper for spade connectors or terminal lugs and stuff like that in there. This is a super cheap one. Second wire stripper. This is an old one from my dad, also an Ipex or Knipex, whatever pronunciation annoys you the most. These are adjustable with the screw to a certain diameter. With some wires in automation, these work better than the stripbucks. That's everything in the main compartment. Apart from this one, I keep a bunch of Vago 221 terminal blocks in here. These are very nice. They have this little lever on top. You put your wire in and then boonk, you lock it. These are super reliable, way better than the screw terminals that you used to use in house wiring, and also better than wire nuts. Not very cheap, but extremely reliable and to code. Just keep a handful of them in the bag when I do wiring in the house. On the outside pouches, screwdrivers, 2 sizes of plus-minus screwdrivers. These are a weird mix of a posi drive screwdriver with an extended blade out to the side. I will zoom in a second. For those star screws that you find a lot on electrical connections. 2 sizes, they are made by PB Swiss tools. Not very expensive, but super nice to not strip out screws. 3 sizes of flat blade screwdrivers, extreme small one for small terminal blocks, and screwless clamps to press down the lever. Super fine scissors. These are like surgical scissors, nice for cutting shrink wrap and stuff like that. Knife. Tajima box cutter used for removing the outer insulation of cables. and also for cutting everything. Pens, some pliers, flush cutters for zip ties. These are just regular side cutters that I surface ground flush, but you can also buy flush cutters. Needle nose pliers, and a regular pair of small side cutters for everything else, basically. I wouldn't cut a 5 times 1.5 square millimeter wire with it, but for everything in automation, this size does nicely. Some zip ties. And that's it. That's my very basic setup that I keep in this bag when I need to do a little bit of wiring. A soldering station doesn't go in there. Yeah, I know that battery-powered soldering irons exist and people love them, but in that regard, I'm fairly old school. The old Weller VECP20 serves me nicely, despite not having a tip that's heated all the way up. The heating element is somewhere back here, and these are kind of sluggish and slow, and also when you try to solder thicker wires or connectors, they run out of steam quite fast. But it's a nice iron. My dad got this from his day job. They sorted them out. It was already in industrial use for like 20 years, and so nice to keep around. A JCB iron with a heated tip would be nicer and more powerful and more modern approach, but this does well for me. That's it. That's basically all I need for wiring. So here are the specialty screwdrivers. They're a hybrid out of a Phillips screwdriver and a large flat-bladed screwdriver, and you need those to not drive yourself mad with these type of screws that are. The idea behind them is you can use a Phillips screwdriver or you can use a flat blade screwdriver. Reality is using a flat blade screwdriver sucks anyways, and using a Phillips screwdriver on these sucks too. And these screwdrivers, I think they call them plus minus geometry. This style of screwdriver really has a positive grab on these screws. They really fit in there absolutely perfectly, and as long as you put in enough axial force to prevent camming, means the screwdriver walks over and damages the screw and the tip of the screwdriver, you can really bear down and get some torque into the screw. The larger one fits, for example, contactors, circuit breakers, stuff like that. And the smaller one, they only come in 2 sizes. And they also make driver bits with a 1/4-inch hex shank that you can put in your cordless drill. The smaller one fits things like the screws on a sub-D connector. So super useful. And if you have to do anything with electric appliances, electronics, automation, I beg you, get those 2 screwdrivers. And you can thank me later. Here is the number. So PB Swiss Tool is the manufacturer, and I think PB 5180.2 and 0.1 are the number for the screwdrivers. You can freeze frame and search that yourself. I'm usually not linking to products because I don't know where you live and where you can buy stuff. So that's your own homework. So even on this cover for this junction box, we have the same style of screw. And here the larger one fits very nicely. And really gets a good bite on the screw without damaging it. These die-cast boxes that I have chosen have a nice O-ring seal around the lid and should be 100% trouble-free. I pulled the Z-axis plate of the machine in order to drill the holes to mount the spindle. The spindle mounting just requires 4 M6 holes. The spindle has 2 dowel hole pins to pin it in place, but that would require to 100%ly know the alignment of each of the components to each other to be able to securely put the dowel pins in and have the spindle, when placed on the dowel pins, be 100% square. And that's a little bit much of a stack up to get right. So I'm just bolting it in place, which is a very common technique. On Datron machines, for example, the spindle is also not pinned in place. In fact, on a Datron M10, the spindle is on a kind of a trunnion, so you can tilt it even with some set screws. So that's not an absurd technique now. Using the dial test indicator to find the center of the plate, finding the low spot on this side, lowering the table, spinning the indicator 180 degrees around, and doing the same on the other side, and doing that as long until the indicator reads on both sides the same. Then the spindle is in the center of the plate, which already is. Now we switch to a spot drill. Spot drilling all the hole positions with a spot drill. As you can see, the work is propped up on 1 to 3 blocks to clear the guide rails off the table of the mill. Tap drill for an M6 thread, 5mm diameter, using a little bit of flood coolant to keep the drill happy. And hand tapping the 4 M6 threads for the spindle, using a spiral flute tap which pulls the chips back out the hole and doesn't push them ahead into the bottom of the hole. Putting the C-axis plate back onto the machine, making sure the rails are clean. Lining the rails up with the guide blocks. When you do that, you have to make sure that you don't damage the wiper seals on the bearing blocks. And once it's started on the first set of blocks, you can just drop it in. Cleaning everything before I mount the spindle. Get the coolant out of the bores. And also wiping away my layout marks with some alcohol. The screws are supplied with the spindle, and there are normal internal hex cap screws, but they have a captive washer on them, so that's very useful, so you don't have to fight the washer moving forwards all the time. You can just hang the spindle over the screws and over the washers, and then tighten the screws through the angled holes in the spindle. The idea to tram the spindle is, first you put an indicator on the Z-axis and you check against a square on the table if your Z-axis moves straight to the table. That's important for the following steps. Otherwise you have to shim the Z-axis blocks or rails. And then you need to tram the spindle itself to the table or to the ways of the machine, depending on how you want to do it. But currently, since I don't have moving axis drives, I'm just rough aligning everything by sweeping the table. I have a dial test indicator and an HSK holder, and I already got the side to side figured out. I just tightened one of the bolts, and then I used a rawhide mallet to tap the housing of the spindle around until I get a 0 reading on both sides. It's 0 over here, and when I sweep over, and we have a 0 over here too, and that's like almost 200 millimeters. Yeah, that's a sweep of 200 millimeters. And I can't do a 360-degree sweep because the block of wood back there, but I can also sweep to the front here and get a 1, 2, 3 block in here too. And that's 0 too. But it wasn't like that when I mounted the spindle. I had to put 80 microns of shim be under the rear screws of the spindle to tilt it forward slightly. And that's because the C-axis plate has a little bit of taper to it. I'm not entirely sure how that happened. Probably when they milled the alignment slots for the rails themselves, something got out of whack. Temporarily I have shimmed it, but eventually I will grind or mill a step, or more or less a taper in the area where the spindle rests against the C-axis plate to get my tram correctly. I could shim it permanently, but shimming is a little bit tricky. You always introduce a little bit of stress. But that said, even machine builders like Kern or DMG, Mori, or people like that rely on shimming components. I know of one of the highest end CNC machine builders who shims. On VMCs you usually have a cartridge spindle with a flange, and they shim under the flange to get the tram of the spindle 100% true. So shimming might be frowned upon, but real world is not perfect. Everything that's getting built has tolerances to it, and we have to deal with them every day. So the moment you free yourself of the idea of perfection, you will sleep better. I wanted to give you a rough difference between the moving gantry CNC and the epoxy frame fixed gantry machine, just in regards of stiffness. I have done very nice work on the CNC router. You have seen some of the work I did on it. It really does well in aluminum and softer materials. It can do steel if you have patience and stay with the cutter diameter below 5 millimeters. Then it's absolutely viable to do high-speed machining in steel. But just comparing the stiffness, I have the C-axis on this machine about halfway. It's in the center of its travel. So it's not the best condition, but also not the worst condition. Let's get an indicator. And I'm just going to take my thumb and press with all the force I can exceed with my thumb. This is of course super unscientific because there is no measured scale, and you have to trust me that I'm using roughly the same force in both cases. So just going to push against the frame or against the spindle up front here. And I can easily bend the machine by, let's say, 70 to 80 microns, just by pushing with my finger. This is with the spindle all the way down, which is a very rare case, or impossible case, because crash. And also, this is still without the cover over the C-axis. With the machine I got a cover that's bent out of, I think, 5 or 6 millimeters thick steel which adds stiffness to the C-axis plate. The C-axis plate is only 22 millimeters thick, so it's basically a leaf spring running on two size 20 linear rails, which is not ideal. But when you add some ribs to it, in this case it's a full enclosure, it stiffens it up against bending and also against torsion. So that's very nice, but I have to see if it fits over the Spinargi spindle. Otherwise, if the cover does not fit over the spindle, which in theory it should apart from the plug, which I have to do a small cutout, at least according to the CAD drawings. Otherwise I can still, instead of doing a full housing, I can bolt on two ribs on the side of the C-axis to increase the stiffness. But we will see if that's necessary. I hope I can use the full cover. Also, it's easier to clean a full enclosure than having the ribs with the spindle in between. I have that arrangement on my CNC router, and when you have the oil mist from the minimum coolant system and fine chips, that clogs everything up and it's hard to clean. Same test again here on the new machine with pressing with full finger force against the spindle. I get maybe 20 microns out of it. So that's a significant difference there. And here we are, first mill tests. I have a piece of 60 Rockwell C hardened tool steel, and I just modeled up some geometry in Fusion 360, and I'm using a 1mm 2-flute ball end mill to cut this geometry into this piece of hardened tool steel. And I have to say, the little machine does really nice. It behaves very well with these small cutters. I'm taking a depth of cut of 50 microns and a step over of 50 microns too. And this is my roughing strategy, and I'm leaving 20 microns of allowance for finishing. For finishing, I'm just walking down the contour with a 50 micron step down, cutting it to nominal, and you can see the reflection of the cutter in the finished wall section of the profile that I'm cutting. So that's looking very promising. Changing the cutter to a 2.5mm 2-flute end mill. This is a specialized hard cut end mill for hardened materials. The other end mill was just a regular coated carbide end mill for normal steels and high strength steels. This one is specially coated and has a special geometry for hard milling. And as you can see, I'm boring 2 holes into this piece of tool steel without a problem. One is a 4mm bore and the second one is a 3mm bore. Both are cut with a 0.05mm pitch helix toolpath, so I'm just spiraling down the cutter into the material. This is 60 Rockwell C tool steel. This is a drop from the wire EDM machine. And as you can see, I did some 3D profiling on this sawtooth profile, right into hardened material. I cut a 2mm wide slot here, and I did some bores. I don't want to talk precision yet, but these bores were programmed to nominal size, no diameter compensation, and this is 3mm pin. This wants to start, the bore is definitely tapered to the bottom, which is a very, very common problem when hard milling bores. And this one, yeah, it wants to start the 4mm one, but that's already very promising in my book. Hey Stefan, do you want to put a tool length probe in the machine? The answer is no, not at this point in time, because since this is a spindle with an HSK interface, I can use the height gauge to check the length. The nice thing about HSK is it's dual contact. You have a taper, and you also have this face. And this face makes contact with the face of the spindle interface, and you can use that to check your tool length. And a very, very simple way to do it is to reference off the spindle face. So I have a flat bottomed probe in the Tesa height, and the tool holder is sitting on those two blocks, which are matched pair ground to same height. And I pick up the height of these blocks as 0. And then I move this whole contraption over, and I just measure the height of the cutting edge, 77.733. And that's what I would enter as a length offset into the CNC controller for tool 13, which is an 8mm end mill in my world. So for that reason, right now I don't need a tool presetter or a tool length probe in the machine, which only takes away place, and this is more accurate than any tool setter that I can afford. This is just a little test cut to give an idea about the potential when cutting aluminium. 16mm depth of cut, 2mm engagement at 1000 millimeters per minute. This creates quite the chip volume, and I don't want to do further tests without an enclosure. How did you get that machine, after purchasing and moving it into your shop, up and running so quickly? Well, here's the answer. Pushing the machine into place. This is about 230 kilograms. The machine stands on some pieces of sheet metal, and this makes it slide very easy on my wooden floor. These are the first production parts that I'm running on this milling machine. These are some ring-shaped mirrors, and they need some hole work done to them. I used to do this on the Deckel FP1 mill and also on the drill press with a tapping head, but I figured the new CNC mill can do that too. So here I'm drilling, pre-drilling all the holes with a PCB drill, coming in with a 2-flute carbide end mill to do some counterbores, and also sizing some of the holes to a different diameter. If I had some cooling option on the machine, I would interpolate the holes directly into solid without pre-drilling, but it's easier that way. 2mm ball end mill for the chamfers. Didn't have a chamfer cutter that was suitable for the task, so I just interpolated the chamfers. M3 thread with a thread mill, single point thread mill. You just go down into the bore, and then you do a helical interpolation at the thread pitch out of the bore to create the thread. Since this is a very long and spindly tool, I'm doing a spring pass. Checking with a thread gauge. And for the second side, I'm creating a little fixture because this is a repeat part that will come up a few times a year, like 50 or 60 times. Just taking one of the brass blanks for the ITS chuck, and I'm machining a little bit of contour into it and 2 dowel pinholes with a 2-flute end mill. Boring a central hole for a thread. I had to hand tap the thread because I didn't have a suitable thread mill that size. Again, the same 2mm ball end mill to do some chamfers. Checking the dowel pinholes with a 3.99mm gauge pin. Pins pressed in, and the part that we previously drilled and milled fits very nicely over those pins. The holes that I milled in the previous step are plus 2 microns oversized, so they are a nice sliding fit on the dowel pins. And from this side there are just 2 counterbores milled. I could do it on the drill press too, but I figured let's have the robot do it. And here is the finished product. Oh, by the way, I'm wearing gloves because I'm cleaning parts at the same time that I'm running the mill, not because I wear gloves when I run a machine. I already stocked up on the brass blanks for the ITS chuck. These are literally just blanks. They're machined all around out of brass. And they have the sheet metal locators, these guys, and the feet already mounted to it. The only thing that you need to add is a draw bolt. Didn't buy draw bolts extra because those are very expensive. I also got 5 sets of the sheet metal locators, which is always the lower sheet, the locator sheet, and 4 of the feet. And these parts allow you to make everything that you have in your shop and that you can drill holes into to make it ITS chuck compatible. So that's the locator sheet. Let's go to the chuck and look how this locates. When we look at the locator sheet, when it drops on the 4 spigots, it's already aligned very well. It's really completely free of wiggle that way. And now imagine that you pull it down and then everything deforms elastically and seats itself very precisely. You can see that on an ITS holder if we put it on the chuck, pull it in with the draw bolt. The lower sheet is the locator sheet, and the upper sheet is just to give clearance. When I tighten the ITS chuck now, see what happens. The locator sheet deforms. And that's what creates the locating and averaging effect that makes the system so darn precise. And when we look very closely at those spigots, those are contacting the sheet metal only on the sides. Here, 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 here. On each of them. The front and back are clearance to the spigot in the sheet metal. That's basically how it works. The The spigots are oversized, and you deform everything, and then it gets squished in place. As brutal as it sounds, but it works extremely well. And I'm not saying that it works extremely well because I played 2 weeks in my shop. I'm saying that because it's an industry standard running on thousands of machines out there. My personal experience with this system is extremely limited. I basically know it from my day job. We had it on the RAM EDM and a graphite milling machine to cut the electrodes for RAM EDM, and also work holding for the EDM, and also the measuring machine, the coordinate measuring machine to inspect the work, and the electrodes had the ITS chuck on it. As you can see, I built an enclosure out of cardboard. I think that's a good way to figure out the shape and the overall form factor and the usability of the machine enclosure before I commit to purchasing several hundred euros of Lexan and aluminum extrusion to build this contraption. And I'm seeking a little bit of experience from my previous machine, where I also had a kind of open enclosure, open to the front with these large beveled edges. And also from a small machine that we had at my day job that had also exactly the same form factor. It was also a fixed gantry machine, but it had a door on the beveled section that hinged upwards. Currently I have it down here, and I suspect that for 99% of my work that I do on this machine, or expect to do, you never know what you're going to do, in this configuration with the door open, it will contain most of the chips, especially when I run small end mills like 1 to 3 mm end mill or do engraving. But if I have larger chip volume to remove, I can just hinge up the front door. This will of course all be transparent Lexan. The issue with an upward hinging door is you need to get it farther forward so the hinge point is in front of the spindle, and also that's quite the swing to move up, and you can't get with the head in anymore. You will bump your head on the door up there, and just creates a whole array of problems. And also chips are raining down on you when you're with the head in there and trying to align something. The downward hinging door has other set of problems. Chips will get stuck to the inside, especially plastic and very light aluminum chips when you run minimum quantity cooling. And the chips, once you hinge it down completely, will fall down onto you. I could also go with a vertical wall, skip the bevels, and make a sliding door that slides down out of the way. The problem with that is that creates a very, without these bevels, this enclosure looks very bulky, and I don't like the overall look of it. And same problem. And then with a sliding door, you create another set of problems. You have to seal the chips on the sliding surfaces with brushes or something like that. So sideway hinging doors, nope, just nope. Those need a lot of space to the side. Sideway sliding door would be super cool, like on a vertical machining center. I think you could do it with one rail and two bearing trucks on here, and then just whoop, slide it out to the side. But that would mean that I suspect I run the machine mostly with the door open. That would mean that I would have always this 800mm wide door out here in the way. Not a big fan. So there's a lot of considerations for a small shop and a machine enclosure. You could build an enclosure or a door that moves upwards. The Datron M10 at my day job had a pneumatic lift gate. The problem with that is it needs a lot of height. The lift gate was about 3.5 meters tall, and I still bumped my head when I got into the machine. So I don't want to deal with that. The open top nature of this enclosure has its drawbacks, of course. Dust will escape, very light chips will escape, but also it means that I don't have to have a huge greenhouse in here. So compromise again. I prefer this open frame style. And here a little glimpse into the glorious world of special machine building. It's a lot of freehand drilling holes with cordless drill. Here I'm drilling the two holes that mount the plate for the X and C axis drag chain. I have my shop vac set up with a small magnetic base, so I don't get chips all over the place onto the guideways up there. That worked very well. That's a fine cordless drill, and the nice thing about it is it spins really fast. I think it's 3000 RPM at the fastest setting, and for small drills in steel or in metals general, that's very preferable. Gives very good progress on drilling. Power tapping M4. When I do something like the drag chain mount, I try to use the same size screw and thread for everything. The mounting plate is mounted with M4 screws, the mounting screws for the drag chains are M4, and so on. And later the zip tie clips will also be held on with M4 screws, so you don't need 17 different wrenches when you take it apart. The tapping with the cordless drill is a little bit of a practice thing. Over time you will get pretty good at it. Made some standoffs out of 14mm stainless steel. Milled some wrench flats on it to tighten them. A little bit nicer than using vice grips to tighten them. And now the connector plate that will hold the X-axis drag chain is screwed on, and then I need to figure out the mounting holes for the drag chain on this plate. And for that I'm just taking the drag chain, putting it in place, and I'm using a clamp to hold it in place, and I'm just transfer drilling the holes with cordless drill, with matching drill. Then I just finish the holes over on the drill press. Transferring the whole location off the drag chain with a matching drill. And on the second hole location I noticed that the drill, or the cordless drill, interfered with the C-clamp that I was using, so I'm changing to one of the can twist style clamps, which has a lower profile and doesn't interfere with the drill or the drill chuck. And that's basically the whole day when you build a special machine. holding stuff together, figuring out where things go, and bolting it together. Over at the drill press, drilling and power tapping the holes for the drag chain. You can plan and lay out everything in CAD, yes, and usually that's what's done in a professional environment, but still we had to do an awful lot of on-site and on-machine drilling, tapping, and we also did a lot of a lot of cutouts in the machines with jigsaws, with a router, or with magnetic drill press. I have one piece of drag chain going to the x-axis, and then there's this riser block and this mounting plate where the x-axis drag chain mounts to. Then I made the sweeping loop with the cables up to a second drag chain going to the z-axis. And when we jog the axis up and down, you can see how the cable and the drag chain rolls up and down. I took one of the brass blanks, measured the whole pattern, and I drilled it in a piece of, this is O2 tool steel. Drilled it in. I had to add 4 holes on the outside because I'm using, this plate is larger, and it would interfere with the 100mm locator pins on the chuck, so I have to drill clearance holes out here too. And as a quick explanation, the large 10mm holes here are just clearance for the spigots to poke through. The central M10 thread is for the draw bolt. The 4 M5 threads here are only to hold the feet. And these 2 holes are the only holes that need some kind of precision in location. These are 4mm dowel pin holes, 4H7 for a nice slide fit on a undersized pin. I'm using carbide end mill shank because these are ground mildly into minus tolerance, so they fit into your collets. And that's all the features you need to mount to make something Aerovo compatible. Then you take your 2 sets of sheet metal. They have dowel pin holes in them. By the way, these are just punched. They are not wire EDM cut or ground or something like that. They are just punched. You align them. Then you take the second layer, you put it on top. Then you take your pin, poke it through, align it on one corner, and you align it on the second corner like this. And you make sure that everything is clean, especially from, I did a half-assed surface grinding job on these to clean the factory Blanchard grind up. So you stack them and you align them. And then you can bolt in the feet. And the feet not only act as feet, but also they hold the sheet metal in position. Then you tighten them to a medium gronk. Then you can pull the pins. And the pins make sure that the locating features are aligned to each other and to your hole pattern, how you drilled it. And then last thing is to add the draw bolt. And you're ready to go. You can put this in the Aerova chuck. This will become just a plate with some threaded holes so I can hold stuff onto it. Or just C-clamp something to it if I need to. There we go. Now we just drop it onto the chuck. Lock it in place. Now it's solidly mounted onto the Aerova chuck. Now we can work on it. The operation every owner of a high-speed spindle mill dreads: drilling. This is a 5mm high-speed steel PM parabolic flute stop drill, and it's behaving relatively nice. I'm running it a little bit too fast and a little bit too slow on the feed rate, but it still breaks the chip nicely, and it held up drilling the 100-something holes into this plate without active cooling. To be on the safe side, I did a full retract every 2mm to make sure that the chip breaks, and in the end it worked out fine. I finished the pallet for the ITS chuck. As you can see, just drops on here with the 50mm system. You saw the machine drill all the 5mm holes. I don't have a thread mill that's suitable for 6mm thread, M6 thread, so I just went to a drill press and used tapping head to do all the 100-something holes. Not terrible, but what can you use this for now? Well, it acts like a 1-2-3 block, just flat. You can, for example, take another block like this one, and bolt it to the side, or bolt it up vertically. Of course, you had to indicate it if you wanted to use it for anything precise. But now you have a large angle plate, basically. And here you can just C-clamp or can't twist clamp a part against it to do, for example, end work on larger pieces. Like this. Say if I needed to do milling on this end of the part, like drilling and threading. So that's one option. And suddenly, customer comes in and, hey, I need some parts. Okay, not a problem. I just take the ITS chuck, take out the fixture, the fixture plate, put in my job specific fixture block, lock it in, make sure that I recheck my 0 on the part, and I'm ready to go just in a few seconds. Or heck, I need a vise, which I don't have modified to fit on the ITS system yet, but it will come. And then I have the customer job finished, the fixture comes out again, and I can come back to my tool room plate here for general use. Also, since it's elevated off the table, I can just take my V-block here, this wonderful thin profile V-block that Adam the Machinist made, and screw it onto the plate and do, for example, end work on round shafts like this one. And heck, the customer comes again and needs parts. Okay, not a problem. Whoop, comes out, goes back in, doesn't need re-indicating for straightness. This test checked for rotational repeatability. If the fixture that I'm putting in the chuck rotates to the same position again. And yeah, it does. And the same should be for the height. Let's drop an indicator on top. It's zeroed out. I loosen the chuck, wiggle it around a little bit. As you can see, it's loose. I can't lift it off because the indicator is hitting the top. Should have put it on the underside. And if I retighten it, it goes straight back to 0 without a problem. The C height on these has to be extremely repeatable because those 4 posts hit the hardened and ground pads on the chuck, and it's there is not much that can go wrong here except for a chip under one of the 4 feet. Okay, then we are done with our end work on this piece of shaft, and we take off the V-block. You can also do regular milling on this plate, either by using small strap clamps, clamp your part down, bolt it directly down onto it, or use small clamps around the edge of it because it hangs over the chuck very nicely. For example, if say you have a piece of sheet metal and you needed to cut parts out of it, you could just clamp it down like this. And then come in. Of course, you would have, if you wanted to mill through, you put a piece of sacrificial material between the sheet metal and a nice fixture plate. This is not meant to be super sacrificial here. I hope I could give you an overview over this machine, its capabilities, how I plan to operate it, how I plan to build the enclosure. And the final iteration of the enclosure will take some time because I want to use it before I commit to expensive materials. Thank you all for watching, thanks for the support, and I'll be back.